function value f of x, where f was a function that took d-dimensional vectors into R. In this video, we're going to do the same thing but add some additional constraints. Previously, we looked at the problem of minimizing f of x. Here, we're going to add in some additional constraints. That is, for real valued functions g sub I, that is, we consider the constrained optimization problem of minimizing f of x subject to gi of x less or equal to 0 for I going from 1 to m. So we associate to this problem what we call the Lagrangian by introducing Lagrange multipliers lambda sub I, which are greater than 0. These correspond to each inequality constraint given by the gi of x's. So here we end up with L of x and lambda equal to f of x plus the sum, where I ranges from 1 to m, of lambda sub I g sub I of x, which we can see is equal to f of x plus lambda transpose g of x. And here in the last line, we've concatenated all the constraints gi of x into a vector bold g of x, and all Lagrange multipliers into a vector bold lambda in Rm. We now introduce the idea of Lagrangian duality. Duality is the idea of converting an optimization problem in primal variables like x into another optimization problem in a set of dual variables like lambda. The problem of minimizing f of x subject to gi of x less than or equal to 0 is called the primal problem, corresponding to the primal variable x. The associated Lagrangian dual problem is given by maximizing d of lambda for all lambda in Rm, subject to lambda greater or equal to 0. Here, lambda is known as the dual variable, and d of lambda is the minimum of all x in Rd of L of x in lambda. Assuming that f and g are differentiable, we find the Lagrange dual problem by differentiating Lagrangian with respect to x and setting the differential to 0, solving for the optimal value. In order to solve the Lagrange multiplier problem, we need to follow the following steps. We need to solve the following system of equations. The gradient of f of x is equal to lambda times the gradient of g of x, and g of x equals k. We need to plug all solutions from the first step into f and identify the maximum and minimum values, provided they exist, and that g of x is non-zero at this point. Now let's think about this in terms of a three-dimensional vector x. So when we look at this, it looks like there's only two equations. In fact, if you have n variables, it's actually n plus 1 equations. Our first equation, in terms of gradients, if x is x1, x2, x3, we really have the derivative of f with respect to x1 equals lambda derivative of g with respect to x1. Then the derivative of f with respect to x2 equals lambda the derivative of g with respect to x2. And then the derivative of f with respect to x3 equals lambda the derivative of g with respect to x3. And that g of x is equal to k. So with three variables, we're actually going to have four equations and four unknowns: x1, x2, x3, and lambda. As a final note, we need to be careful with the fact that in some cases, minimums and maximums won't exist, even though the method will seem to imply that they do. in every problem, we should make sure that minimums and maximums will exist before we start the problem. We should also note here that while the given constraint is going to be g of x less or equal to k, we solve for g of x equals k because, as you can see on the picture, as we move the parabola up and up and up, we end up with a parabola that'll be tangent or equal to g of x for our optimal solution. In this example, we're going to find the maximum and minimum of f of x and y equals 5x minus 3y, subject to the constraint x squared plus y squared equals 136. Now, before we begin, it's important to check critical points and the boundary cases. Here we have no critical points, and it turns out that if we look at the boundary, x squared equals 136 and y squared equals 136, the root of 136 is about 11.7, and f of 11.7 and 0, and f of 0 and 11.7 will turn out to neither be maximum nor minimum values. From these equations, the gradient of f equals lambda the gradient of g, we get the vector 5, 3 equals lambda 2x, 2y, and that x squared plus y squared is equal to 136. From our first equation, we can solve for x. X is equal to 5 over 2 lambda. Our second equation, 3 is equal to lambda times 2y. We solve and get y equals negative 3 over 2 lambda. Plugging these x and y values into the second equation, we end up with 25 over 4 lambda squared plus 9 over 4 lambda squared equals 17 over 2 lambda squared, which is equal to 136. Solving for lambda, we get lambda equals plus or minus a quarter. Plugging that into our x and y values gives us negative 10, 6 and 10, negative 6. Those values into our function f give us a minimum value of negative 10 and 6 and a maximum value at 10 and negative 6. In this example, we want to find the maximum and minimum of f of x, y, and z equals x times y times z, subject to the constraint x plus y plus z equals 1. Here, x, y, and z are all greater or equal to 0. So again, we solve the gradient of f equals lambda times the gradient of g. That gives us the equations xy equals lambda, xz equals lambda, and yz equals lambda, as well as the constraint that x plus y plus z equals 1. So from the gradient equation, we know that if yz equals lambda and xz equals lambda, then zy has to equal xz, or that z times y minus x equals 0. We'll see here that z then equals 0, or that x is equal to y. Notice that we can repeat this with any combination of two of those three equations. Now, if z is equal to 0, we get either the equation, or either the point 1, 0, 0, or 0, 1, 0. If x is equal to y, we get the equation 0, 0, 1, or a third, a third, a third. We can see that the first three options, 1, 0, 0, 0, 1, 0, and 0, 0, 1, we have f of x equals 0. Well, the other one, we have f of x equals a third cubed, or 1 over 27, which will be our maximum. Remember to check your boundary cases. That's when x, y, and z are all 0. And then again, when x equals 1, y equals 1, and z equals 1. And of course, we cover all of those options in the solutions that we have. In this example, we want to find the maximum and minimum values of f of x and y equals 4x squared plus 10y squared, subject to the constraint x squared plus y squared is less than equal to 4. We do have a critical point in this example, and it's easy to find that that critical point of f is 0, 0. So we'll need to keep that in mind. So when we solve gradient of f equals lambda times gradient of g, we get 8x and 20y is equal to lambda 2x and 2y. Again, with the constraint x squared plus y squared equals 4. From the first equation, we get 8x equals lambda times 2x. So we'll rearrange to get 2x bracket 4 minus lambda equals 0, which gives x equals 0 or lambda equals 4. Taking those points and plugging them in, we end up with 0, 2, 0, negative 2, 2, 0, and negative 2, 0. A similar analysis on the second component, 20y equals lambda 2y, will actually give us the same set of 4 points. And so we have a minimum value at our critical point, 0, 0, and maximum values at 0, 2, and 0, negative 2. In the next video, we're going to talk about functions that are convex, how to optimize if that's the type of function that we're working with.